Hello, my name is Justin McAfee. I am the founder of Wright One, and today I really just want to tease your minds a little bit in terms of the problem that we're facing with eVTOLs as we move forward. Why don't I go ahead and actually just tell you what it is that Wright One wants to accomplish in terms of the maneuverability concepts, as well as our particular goal for giving freedom to pilots and operators working in the field. Just to give a little bit of preface, we have a FPV drone pilot. This is the particular drone. It is a 5-inch blade configuration with a camera, and this is the pilot. This is Alex Vanover, also known as Captain Vanover. He's putting on FPV goggles, which are basically first-person viewer goggles. And this is the maneuverability that we're looking to achieve with the Wright turbine. Unfortunately, I can't actually give you any clear definition or graphics, so apologies in advance. But when it comes to this type of maneuverability, not only are you adjusting the flight mechanics on the aircraft, you're also adjusting the airflow across the propellers. And for turbines, this becomes a little bit of a nuisance because it's non-uniform airflow. And that's what we're going to talk about today in terms of the issue and the problem that is being faced when it comes to propulsion modules that these pilots or these operators are currently seeing. So just in comparison, very quickly, the nearest aircraft that we have today that can achieve maneuverability somewhat similar to this for a person is an F-22 or an F-35. All right, now that we're back, why don't we go ahead and actually talk about the particular problems that are facing turbines today? This is a standard turbine, and you basically have the cold section and then you have the hot section. Let's go ahead and start with the cold section first, though. It's at the very beginning, air comes in, it gets repeatedly compressed through a series of stages of fans, one after the other. Every single fan stage is operating on a central shaft, which means that every single one of your fans only rotates at that RPM. There's no way for you to tailor the RPM, which means that you need uniform airflow rate through the turbine at all times. Otherwise, you get something called compressor surge. Compressor surge is basically like an air bubble inside of the turbine, and it reduces the performance completely to the point where there's actually a loud bang that occurs. And sometimes this occurs on commercial turbines. It just usually signifies that something like a bird strike occurred, or maybe the engine ingested like fragments of a tire on the runway, or it could be any number of things that occurred. But the thing to note here is that whenever something gets ingested into the turbine and compressor surge occurs, you're done. The whole thing, the whole engine is done. And the other thing that you need to recognize as well is that when air actually enters into the turbine, it gets curled with the first rotor system. That's what you see when it hits the first fan stage. So when it hits the first fan stage, the air curls and then it gets corrected with the stator system that's right behind it. That's why there's always two fan stage blades. And the only reason why we've got a stator behind it is because we need to correct the curl on the air before it hits the next rotor. Otherwise, it looks remarkably similar to this. So we've basically manufactured contra rotation without the counter rotating fan stage in traditional turbines today. So if you look at this eVTOL like Jetson 1, you have two sets of propellers. One is rotating in one direction and the other one is rotating in the other direction. This means that air, as it flows through, it actually gets corrected. But with open prop designs, these speeds are only good when it comes to 0 to 130 miles per hour. They're not great for 150 to 350, which is typically reserved for turboprops or turbines. And there's a reason for that. Whenever air actually hits a blade, it gets slipped off. So the lift that's being generated by the prop is then actually slipping off the tip of the blade. And that's the reason for some of this correction with the curl. You can actually see that in these two instances below the Jetson 1 craft. So if you have the two axial fans in series, you can actually see the dispersal is more conical in shape. Versus if it's contra-rotating, then you actually have a more focused column of air. It generates better thrust capability. All right, so now that we've actually gone through a couple of these issues, there's only one other thing that I really want to highlight at this current point in time, and that's really the business side of turbines. Turbines are costly motors today. How costly? Well, here are some of the most recent programs that we've actually seen. And these are just the R&D costs in terms of $2 billion for a program, as well as $10 billion of the program. And you can also see the cost of the engine as it actually gets installed onto the aircraft and the percentage of that cost. How much the airplane costs in total, and then what the engine percentage is for the cost of the entire aircraft. It's around 20%. But this doesn't really actually signify the entire business model, because most of these companies, what they end up doing is they actually just put the engine onto the wing of the aircraft at cost. So they don't actually make any money off of the sale of the engine to the aircraft. I mean, remember, this is a long-term business relationship. These aircraft, some of them are still like MD-80s that are from the 70s. Like these bodies, they stay in service forever. And that's what is the typical sales cycle, especially for these turbines. And that's what it ends up making sense in terms of actually developing these specific engines for these particular aircraft forever. So if you look at the sales cycle, you're basically spending all this money in terms of R&D, and then you put it onto the wing, and then it starts to actually recoup a profit. But you look at this from a 50-year sales cycle. So whenever engine manufacturers start to see issues on their particular engine, let's say that it's the Boeing 737 MAX, then you start to say, well, what ended up happening? Well, I mean, the manufacturer actually came out and said that they were looking to actually improve on the current body from a legacy body. They didn't actually change the body at all. They just changed the engine. They made it a higher bypass ratio, which then shifted the center of gravity, which is the reason why they placed the one mechanism to be able to actually detect whether the airplane was entering into a stall, and why it was actually starting to force the airplane down. I mean, all of these things really attribute to the aspect of we have an engine system. It is developed for a particular aircraft, only that aircraft. As it moves into service, and it's only for that use case. We need to shift away from that thinking, especially as we're going into now eVTOLs. All right, so let's just go ahead and recap very quickly before we actually move on to the solution of Wright One. There are a few problems that are being faced in terms of eVTOLs today. And as I highlighted in a most recent LinkedIn post, there are two aspects that really are crucial when it comes to developing these craft. There's the propulsion module, which we need to reinvent. This isn't like reinventing the wheel. We just need to come up with a unique solution for eVTOLs. I mean, we're not flying across the country anymore. We can't just have the efficiency be at cruise flight. We have to have the efficiency be high for all stages of flight. And then the second issue is battery density. Wright One only focuses on the propulsion module. We don't focus on the battery density. But the research that I've been doing in terms of battery density is that we're getting pretty close in terms of being effective enough to actually create the crafts that we need in terms of actually moving eVTOLs forward. So looking at the problems that we're facing with jet turbines today, we have to have a decentralized solution in terms of power distribution across fan blades. It can't be an open prop design. It has to be a ducted design. Much like jet turbines. However, unlike current jet turbines, the fan stages need to be able to actually correct curl. And Wright One is thinking that this should be done through a contra-rotating system. The other aspect is that this this turbine system has to be reduced in terms of cost. It has to be substantially cheaper as compared to current turbines of today. The cheaper turbines that I'm thinking about, like general aviation turbines, there's the Catalyst, and then there's also the widely successful PT6. These turbines are cheap. They're about 1.4 million to 2 million, depending on the configuration that you're looking for in the shaft horsepower. However, these engines need to be substantially cheaper, and they need to be more widely distributed, especially if eVTOLs are going to be commercialized for the future, and we're going to become an airborne society. So what we've come up with is a modular, customizable, expandable platform for all eVTOLs. And we don't have to actually go through an R&D program or project that costs billions of dollars for one specific aircraft to be able to put it onto your airframe. It could be any type of airframe. And all we would need to do is we just need to figure out or configure the particular nacelle, as well as the fan stages that you could slot into each individual nacelle to be able to get the customized performance that you're looking for your craft. That's the uniqueness. That's the value proposition of Wright One. No longer do we have to have so much dedicated to one solution for one aircraft. Wright One has actually done all the R&D effort up front. And now we can actually just place it in terms of customizable performance across all eVTOLs moving forward. And that's what we're going to get into in terms of the solution with Wright One and the Wright turbine.